on today. Since I have been knowing Muxin for a long time, and I'm hosting him during his sabbatical here. Muxin comes from Florida Atlantic University, and he will be visiting here for a month. The plan is that he will be back also in spring. And Muxin is originally from China, studying there at Beijing Normal University, but then he went first to Louisiana for his master, then he did his PhD with Thomas Timani in Germany, and then he went to Marseille, to Erlangen for his postdocs, and since 2015 he is a professor in Florida, and we're with Muxin and with a colleague, Jonathan Engel, there was this new group of loop quantum gravity that in fact is going to host the next big loop quantum gravity conference in less than 2 years. So Muxin is one of the persons who worked most in the current, even though he started with the canonical of the theory, one of the persons who contributed the most to the understanding of transition amplitudes in quantum gravity in this so-called Spinfoam formalism. And one of the signature results from Muxin is the introduction of the cosmological constant in the theory. And for years I have been struggling because the construction he introduced, he worked on, used the quantum groups. So for years I have been struggling trying to, as a humble physicist, I tried to understand quantum groups that use. I couldn't, despite many courses by Muxin and so on. And now Muxin is coming here and say, oh, look, I have a simpler version of this beam, just using Simon. So
okay.
Let's hear
Thank you for the introduction, and it's really nice to be here, and thanks Francesca for inviting me. And it's great to come to this nice campus, nice building, and interact with mathematicians. Okay, so you can see the title. I'm going to talk about spinfoam quantum gravity with cosmological constant. So maybe just first give you a little warm up and give you some idea of what is quantum gravity and what is going on. So this is basically So this cube summarizes all the physics theory or framework that we have so far, and basically everything is controlled by 3 parameters: and G Newton, the gravitational constant, and speed of light, and h bar Planck constant. Yeah, and you can see that you have different corners of different theories, and the origin is just the classical mechanics, Newtonian mechanics, and then you can turn on either h bar or G Newton or speed of light. You can have Newtonian gravity, special relativity, quantum mechanics. Yeah. And then you can be more brave and turn on 2 parameters at the same time. And you can turn on h bar and speed of light, and you get quantum field theory. And you can turn on G Newton and speed of light, you get general relativity. And you can turn on h bar and gravitational constant, and you get some non-relativistic quantum theory of gravity. But what so far in physics, what we know very little, and the place in this corner in this diagram that we know very little is actually this red dot, this red corner, and which is the fully fledged relativistic quantum gravity theory, and it contains all the 3 parameters: G Newton, speed of light, and h bar. So this basically the most fundamental open problem in physics so far is to how to formulate and how to understand quantum gravity, and this is what this talk is about. And here, at least, the most of the approach in this world on quantum gravity. Okay, and of course, in this talk, I'm going to focus on the loop quantum gravity approach. Okay, so I'm going to give a definition of loop quantum gravity. In this talk, I try to be as rigorous as possible. So this is the definition of loop quantum gravity. So loop quantum gravity is a background independent and non-perturbative approach to quantum gravity in 3+1 dimensions. And here there are 2 defining features. First, background independent and non-perturbative. And these 2 defining features defines loop quantum gravity. And here I'm going to talk about and explain these 2 features. So firstly, what is background independent? It means that we consider quantum gravity as a quantization of space-time geometry. So this is just, we learned from general relativity that space-time is actually, gravity is actually curved space-time, equals to curved space-time, okay? So then naturally, quantum gravity is a quantum space-time geometry, okay? And we say, why we say it's background independent? Because we know we call background is space-time. Space-time is the background. And then we are talking about gravity, and we are talking about the dynamics or the quantum theory of space-time itself. And then it should not depend on priori a space-time structure. So that's why we say this is a background independent. And then practically what we do is we take some manifold, 4-dimensional manifold. So here I can only draw a lower dimensional manifold, but what they are working on is a 4-dimensional manifold, and we consider quantum space-time geometry on this 4-dimensional manifold. And this quantum geometry has a feature which is discrete, fundamentally discrete. And here we model the geometry by using a 4-dimensional triangulation and define the quantum geometry on a 4-dimensional triangulation. So here in 4-dimensional triangulation, this is what we call a simplicial complex. And the building block of the triangulation are what we call a 4-simplex. And this is, you can see this is the simplest 4 manifold, and which is the building block of any 4-dimensional triangulation. So this is a projection of a 4-dimensional object on the plane. And you can look at the basic topology of this object. It's very simple. So it is a 4 manifold. The boundary is a 3 manifold, and you collect every 4 points out of the 5, and you get a tetrahedron. So there are 5 possible collection of 4 points out of 5. So then you get 5 tetrahedron. Then you see that this 4-simplex is a 4 manifold. The boundary is a 3 manifold triangulated by 5 tetrahedron. And this is a very simple basic topology of this building block. And so this will be the elementary cell of the triangulation. And then we are basically building quantum geometry on each of the cells. All right, and then what is non-perturbative? It means that we are going to construct the full amplitude of quantum gravity instead of a perturbative expansion. So this amplitude is what we call the spinfoam amplitude. And this the structure is very much resemble the topological quantum field theory. That we have this triangulation, a simplicial complex. It contained objects like the 4-simplex, phases, and tetrahedra, and so on. And then we are going to associate amplitude to each of these objects. So there is phase amplitude, what we call phase amplitude, associated with the triangle. And there is also tetrahedron amplitude associated with each tetrahedron on the boundary of the 4-simplices. And then there's also what we call 4-simplex amplitude or vertex amplitude associated with the 4-simplex. And then this amplitude basically defines the quantum dynamics of quantum gravity. And here, okay, so there is a sum over all the intermediate states. And these states in quantum gravity, we label it J and I. J means some spin, and I is something what we call intertwiner, but they are some the basis in the Hilbert space of loop quantum gravity, what we call spin network states. So this is the very basic structure of the amplitude that we are going to working on. All right.
Sorry.
Yeah.
Independent, are we saying it's independent?
It is still dependent on the triangulation. It depends on the triangulation at this moment. Yes. So in the end, we are going to sum over the triangulation because each individual triangulation, each individual amplitude will depend on triangulation, but ultimately we are going to sum over. Yes. Okay, is there any other question? Yeah.
Like analysis for idealization of the space-time.
Reggie, you mean Reggie calculus? Yes, this is a quantum version of Reggie calculus. You can see that. I mean, it will be closely related to Reggie calculus that I'm going to talk about.
Somebody some description of I should think about amplitude.
Okay, so amplitude are solutions of certain equations. And those equations are basically the quantum, what we usually in physics call Schrodinger equation, and describing the dynamics of the wave function and dynamics of the quantum states. And then these amplitude are solutions of those equations.
This is just a number.
Yes, well, I mean, if you have a closed manifold, this is the number. But if you consider a manifold with boundary, then this is a wave function because it depends on the boundary data. Yeah, exactly. All right, so now let's come to the spin-foam loop quantum gravity with cosmological constant. I like it because this is a nice direction in loop quantum gravity, which has a very nice interpolation with mathematics, between mathematics and physics. Okay. So why we are interested in cosmological constant, and because we are physicists, we know that there is a cosmological constant confirmed by observation. So there is a positive cosmological constant, what in physics we call it dark energy in our universe. And then we have to consider, to really fit with experiment, we have to consider the Einstein equation with the cosmological constant term. So that's why we need cosmological constant. And then therefore the formulation of loop quantum gravity need to include the cosmological constant from the physics motivation. And then so in the theory, we are going to treat the cosmological constant as a fundamental parameter of the theory. Okay? Namely, if we look at the amplitude that I introduced, so it will each part of the amplitude, will depend on an extra parameter, which is the cosmological constant. And the whole amplitude, of course, depends on the cosmological constant. And then an important feature that we will look later on is that the sum over state will have a cutoff. So before, with no cosmological constant, and this sum over the intermediate state will be infinite sum, and sometimes it will give divergence. In some triangulation, this sum will be divergent for the amplitude in the last slide. But then once you impose cosmological constant, once you have a cosmological constant, and the cosmological constant will provide a cutoff, a natural cutoff for the state sum, and make the amplitude finite. The physical reason is that the sum over states relates to geometry, relates to, for example, the scale of the geometry, the area of all those phases. And then this cosmological constant provide a large scale that your area cannot go beyond the cosmological scale. So that's physics motivation of this cutoff. And indeed, from mathematics, you can actually prove that this is indeed a finite sum. And once you have cosmological constant, and this amplitude will be finite, will be well defined, and you can really do rigorous mathematics with this amplitude.
So is there a kind of relation between spin-foam and Einstein?
Yes. So the Einstein equation will be, this Einstein equation will appear from semi-classical limit of this amplitude.
Does this work for
Yes, it will be, yes, it is. Right. All right, so just a moment. Okay. All right, so now let me give a brief outline of the history of this area. Okay, and you can see that this direction has a close relation with mathematics. And so, okay, so the starting of the history is 3D gravity. So all these lessons and all these motivations are coming, most of them are coming from 3D gravity. And there is a well-defined spin-foam model for 3D gravity, because 3D gravity is a topological quantum field theory. And 3D means space-time with three-dimensional manifold. And then in this model, this is constructed by using quantum SU2 group. And this model is famous. It's called a Turgenev-Vero model. And this model, well, this is kind of spin-foam model. So the structure of this model is very much the same as I introduced in the last few slides. And this model is nice because on one hand, it is finite because of the quantum group. And yeah, this quantum group, this Q deformation of the SU2 group introduces the cosmological constant to the model. And so this is finite. The sum is finite. So this model is finite. And then on the other hand, this is also semi-classical consistent. Because like you asked earlier, that how about Einstein equation? And then in this model, you can consider semi-classical limit, what is called large J asymptotics. And this model recovers a three-dimensional Regge calculus, and which is a discretization of general relativity in three dimensions in this case, and with positive cosmological constant in 3D. So this model is nice, being finite and also semi-classical consistent. And actually, this Turayev-Viro model gives a topological invariance on for three manifolds. Yeah. And this model gives us the lesson that the cosmological constant should regulate the quantum gravity amplitude and to make a finite amplitude. Okay. And then people try to generalize the story to 4 dimensions, to 4-dimensional real 4-dimensional gravity. And then, well, the motivation firstly was to introduce a quantum group. So 3D, the structure group is SU2, but in 4D we have to consider Lorentz group. And then we have to consider the quantum Lorentz group and define Spinfoam model for quantum Lorentz group. And there are several models based on this idea. And all these models are all finite because of the introducing quantum group. But the problem is that the quantum Lorentz group is complicated enough such that the semi-classical limit is often difficult to extract. So this is probably not a very much mathematical problem of mathematical rigor, but from physics, we want to extract some predictions. But suppose this model is so complicated to compute, then this is very hard to extract physics from this model. Okay, and then the change comes from some later work about 8 years ago, and we introduced some newer version of the Spinfoam model with cosmological constant. Instead of using quantum group, we use something closely related, which is Chen-Simons theory. Yeah? But we know that yeah, we are talking about 4-dimensional gravity, but Chen-Simons theory is 3-dimensional. Yeah? And actually, this Chen-Simons theory is defined on the boundary of this 4-simplex. Yeah? And you will see why it happens. And then the good thing about this model is that the semi-classical limit is perfect, it's nice. And it reproduces correctly 4-dimensional Regge calculus with cosmological constant and either positive or negative. But the problem is that the finiteness model is not manifest because the definition is not mathematically rigorous because we were using path integral for Chen-Simons theory. But for mathematicians, I guess, I don't know, mathematicians usually hate path integrals by physicists because this is the infinite dimensional integral, which is for most quantum field theory, it is ill-defined. In this model, we were constructing using path integral of SL2C Chen-Simons theory. Yeah, SL2C because in 4D it's Lorentz group. Okay, but in this talk, I'm going to improve this. I'm going to make it rigorous, well-defined, and we are going to introduce the improved model based on this with cosmological constant. And for this model, we have both finiteness. We are going to use the rigorous definition of SL2C Chen-Simons theory. And then we are going to put this model to a finite dimensional integral instead of path integral. And then we are going to show that this model is finite, it's convergent. And then the semi-classical limit also reproduce 4-dimensional Regge calculus with cosmological constant. So then in the end, we are going to get a model which is best analog of a Turayev-Viro model, but live in 4 dimensions.
Without lambda, you find that it's difficult to extract the semi-classical without cosmological constant.
I'm sorry, so with no lambda?
No cosmological constant means it's difficult to extract the semi-classical.
With no cosmological constant, it's also one can also extract the semi-classical limit, but has no cosmological constant. Yes, but just Einstein equation with no. Oh yes, so here lambda is introduced, yeah, because it will give finiteness of the amplitude. Otherwise, the amplitude will diverge. All right, so now let's talk about scheme of this construction. So firstly, I'm going to introduce outline the scheme, and then I will put this construction in a more mathematical rigorous ground. Okay, so here the motivation of the construction is so-called Blibansky formulation of general relativity. This formulation, it relates four-dimensional gravity to topological quantum field theory. So it says that the four-dimensional gravity is the BF theory. This is the action of BF theory. BF theory is kind of simple topological quantum field theory. And it's 4D gravity is the BF theory, and with something called simplicity constraint. It's a constrained BF theory. And this is the action of BF theory. And here I'm introducing I should introduce the notation. So here this B is a SL2C Lie algebra valued 2 form. And F is the curvature of a SL2C connection, called A. And this gamma is a free parameter called Barberi-Emis parameter. This play an important role in loop quantum gravity. And of course, lambda is cosmological constant. And this integral. This is the integration of a top form on four-dimensional manifold, and this is called BF action. And yes, and the equation of motion of the theory is coming from variational principle of this action. Okay. And then what is simplicity constraint? The simplicity constraint, it says that the B field has to relate to cotetrad field on four manifold. And cotetrad field is a one form. It's a Lie algebra valued one form. And this B has to be E by G, plus minus E by G. And this constrains the form of B. So once you insert this simplicity constraint back to BF theory, it's reduced to this action. And this action is a well-known action for gravity called host action. It is on-shell equivalent to Einstein-Hilbert action. Namely, if you consider the variational principle of this host action, you will get some equation completely equivalent to Einstein equation. Okay. All right. So now, once we have those actions, the general procedure in loop quantum gravity to construct spinfoam amplitude is to firstly quantize the BF theory, and then imposing the simplicity constraint at the quantum level. So here we are not going to impose classically the simplicity constraint and then quantize, but here we are going to first quantize the BF theory because BF theory is simple. It's topological quantum field theory, and then impose simplicity constraint at the quantum level. Over all the dynamical fields. So for BF theory, we are going to integrate over B and A. Yeah, B and A, yes.
How you quantize? You take path integral?
Yes, so I mean, yeah, schematically, yes. So here it is, path integral. Schematically, we are going to firstly take a path integral, then, yeah, so it's probably good to talk about here. So here we are first going to take the path integral and integrate out B, okay? But we see B integral is very easy to go because it is just a Gaussian integral. Yeah. So we are going to first integrate out B. This is just a Gaussian integral, and then so once we integrate out B, we get a constraint because if you consider the variation of B, you get this F equals to lambda times B. So it relates the curvature to the B field. Okay. And also perform the Gaussian integral. You get after integrating out B, the Lagrangian become F wedge F because this is just a Gaussian integral. So F, there's one term linear to F. In the end, you integrate out B, you get F wedge F. And this wedge F, F wedge F is analog of instanton number. And it is, this is just a total derivative. This F wedge F is just a total derivative. And by integrating, you can, by using Stokes' theorem, you can put this integral on the boundary. And the boundary integral are just the Chen-Simons theory, just the Chen-Simons action. And the Chen-Simons action is SL2C Chen-Simons action. And there are coupling constants for complex levels of Chen-Simons theory, T and T bar. And so here T is complex. The real part is K. And K has to be integer in order to make it well-defined quantum mechanically. And you see this T is like a package. And it unifies both lambda and gamma. These are two fundamental parameters of the theory, and they are all unified by this complex Chern-Simons level. All right, so here this story is for non-zero cosmological constant, but in case you consider zero cosmological constant, you don't have this term. And then all this procedure, the quantizing BF theory and simplicity constraint give the so-called EPRL spinfoam amplitude. This is one of the popular amplitudes in loop quantum gravity as well. All right, so now, so once we have this Chern-Simons, okay, so here this explains why this relates to Chern-Simons theory. Although we are doing 4D gravity, but once we perform this integral, we project to the boundary. Yeah. We only consider boundary Chern-Simons theory, and then we are going to quantize this Chern-Simons theory and then impose this B equals to E by G to the Chern-Simons theory. Okay, but since B is already integrated out, so there's no B anymore. Okay? How are we gonna impose the simplicity constraint? Okay, because we have when we integrate out B, we get this constraint F equals to B. It translates the constraint B to the constraint on Chern-Simons connection. Yeah, so the constraint on B is the same as constraint on F, or constraint on connection. Okay, and then this equation is a key to translate the simplicity constraint to the quantum Chern-Simons theory. And then if you look into that, you will find the simplicity constraint has two, they are first class components and also second class components with respect to the Chern-Simons symplectic form. And by first class constraint, first class components or first class constraint, it means that they are components of the simplicity constraint such that the Poisson bracket is also a linear combination of constraints. And these constraints, I will call them first class. And the second class constraint means that otherwise, and some the Poisson bracket between two constraints are not vanishing on the constraint surface. In this case, we call them second class constraint. And when you quantize the constraint system, and there's it is well known that you have to be very careful about those constraints wherever you have second class constraint, because for the first class constraint, you can impose them strongly. You have wave function, you have first class constraint, you just let your constraint, quantize your constraint as an operator, act on wave function equals to 0, you solve the wave function. That's a simple way to quantize the first class constraint. But you have to impose second class constraint weakly. And because if you do that, do the same thing as in first class constraint, it's very likely that you will get no Hilbert space. You will get 0, I mean, very trivial Hilbert space. Okay, so here we are going to impose the second class constraint weakly. Okay, so specifically we are going to use coherent state, and I will introduce little details later. But we are going to introduce coherent state for Chern-Simons theory, and then the second class constraint are going to impose on the coherent state labels, because the label is classical phase space point, and then we are going to just constrain the classical phase space. So these are all schemes. Okay, so let's make things more precise. All right, so now let's let's put the BF theory on a 4 simplex. Okay, so this is the 4 simplex. So I have introduced the topology of the 4 simplex. This is a 4 manifold. The boundary of the 4 manifold is 3 manifold triangulated by 5 tetrahedron. Okay, so now we know that once we put the BF theory on this 4 simplex and we integrate our B, we get Chern-Simons theory on the boundary of the 4 simplex. Okay, so we are going to define Chern-Simons theory on the boundary 3 sphere. Yeah, boundary is just a 3 sphere triangulated by 5 tetrahedron. Okay, and then we are. It turns out that it is useful to consider the dual graph of this triangulation. And the dual graph on the 3 sphere. Yeah, and the dual graph means that you have 5 nodes dual to a tetrahedra, and you have 10 links dual to triangles. So this is the sphere, and here these blue lines are the dual graph. Okay, so each of the point here, each of the node here, there are 5 nodes. Each of the nodes here is dual to a tetrahedron on the boundary of the 4 simplex. Okay. And because of we have this constraint relate B to the curvature, and here the flux of B. Okay, and we have to turn on some flux because this B relates to geometry. This relates to cotedral field. B is a key because it's geometry. And then this equation tells us the flux of B equals to the magnetic flux of the Chern-Simons connection on the triangle. Okay, so here basically each edge here is dual to a triangle, and each triangle taking a flux of B. But because of this equation, you are equivalent, it is equivalent to consider the magnetic flux or the flux of curvature on this triangle. Okay, so somehow we have to create some magnetic flux in order to get the geometry, in order to get this B field. Okay, so this motivates us to remove the dual graph from the sphere, okay, and remove the dual graph and the tubular neighborhood from the three sphere, and to create this flux. And in physics, this is called a Aharonov-Bohm effect. That once you have some defect in the three manifold, then it creates magnetic flux. But here it is even simpler because we know Chern-Simons theory relates to flat connection. Yeah, but then if you create some defect, you will get non-flat connection along the defect, and then you get non-trivial curvature. Okay.
Topologically connected, in the sense that they have also a
Yeah, that's right. Yeah, exactly. That's right. Okay, and then usually this kind of manifold has name. It's called graph complement three manifold, and usually it relates to knot theory. And in knot theory, one only consider a single loop and remove the single loop and knotted single loop, and then removing the single loop removing the knot from the three sphere, and it creates so-called knot complement three manifold, and which is used to study knot theory. And here it is a little more complicated. We consider graph, and so remove the graph and the tubular neighborhood give you a graph complement three manifold. And the Chern-Simons theory is actually defined on this S3 removing gamma 5, the graph complement three manifold. All right, so now we are going to quantize the Chern-Simons theory on this graph complement three manifold. Okay, and the quantum Chern-Simons theory is defined on the ideal triangulation of the three manifold. The Chern-Simons theory is a topological quantum field theory, and on the three manifold. And the usual way to construct a topological quantum field theory is firstly to make some triangulation of the manifold. Okay, so here we are going to do that. So specifically, it uses the so-called ideal triangulation. And this picture shows that one of the ideal triangulation, that this three manifold can be decomposed by 5 ideal octahedra. So here, these red are ideal octahedra filling in the three manifold. And each of the ideal octahedra can be further decomposed. So this is octahedra, and then you draw a line in the middle. You decompose into 4 ideal tetrahedra. Okay, so here by ideal means that you are chopping the vertex of tetrahedra. Okay, so ideal means that those quantities, those octahedra or tetrahedra, the vertices are chopped and create a little cusps. In hyperbolic geometry, it means that you have vertices located at infinity. And here you see, if you look into this triangulation, that because of these vertex are chopped, it creates these tubes along the curve, along the edge. Yeah. So that's why you have boundary. That's why you have the boundaries coming from removing the graph and tubular neighborhood. Okay. So here, this gives a triangulation of the three manifold. Okay, so and then we just need to look at the building block, which is this ideal tetrahedron. Yeah, and then the Chern-Simons partition function on the ideal tetrahedron, it is well known. It is some work did in 20 years ago. Yeah, and the wave function or the partition function of Chern-Simons theory, or SL2C Chern-Simons theory, on the ideal tetrahedron is called a quantum dilogarithm. So this is a function of quantum dilogarithm, and here I list all the parameters. It depends on 2 variables, mu and m. Mu is continuous, and m is integer. It's an integer. And here Q relates to Chern-Simons coupling, and here Z relates to both mu and m. Yeah. So basically exponential of mu, exponential of m. Yeah. And here I just use B to another way to label Fabry-Image parameter. Okay, so well, the punchline here is that this function, it is well known, is well studied for Chern-Simons theory on a single tetrahedron.
matrices, not full.
It is, yeah, it is this kind of, so tetrahedron is a three-dimensional simplex. Yeah, and this is like a truncated three-dimensional simplex because you want a defect here, right? And these little truncation are precisely building the tube. So I mean, a good way to understand this three manifold is that it is a subway station. It's a subway system. Yeah? And so here, each of the vertex here is a subway station. And then you have the tube connecting the subway stations, and you are traveling in the tube.
But where does the quantum dialogue come in? Is it very far away from the usual dialogue type of quantum?
Okay, good. So there you can do asymptotic expansion. Okay, so you can take T and send T small, T no sorry. So in this case T large, and then this quantum dialogue will become exponential of the usual dialogue. Yes. So yes, so that's why we call quantum dialogue. So it's a deformation. Yeah, it returns to usual dialogue by semi-classical limit. Okay, and then this quantum dialogue is a meromorphic function in mu. Yeah, so here we are interested in, because mu is a continuous parameter, so we are going to analytically continue this mu, and this quantum dialogue function is a meromorphic function, but all the poles of this quantum dialogue function is a lower half plane and also along the real line. Yeah. So in the upper half plane, the imaginary part of mu is positive, and this function is analytic. Okay. And because of this property, we need to be a little careful because we are going to integrate. We are going to make Fourier transform of this quantum dialogue. When we glue those tetrahedra, they correspond to some Fourier transform. So we have to be very careful because on the real line there are poles. So we have to deform the integration contour such that we don't touch these poles. Okay. So that's the motivation to introduce some other parameter alpha and beta. Okay. So introduce alpha beta positive. Then we are able to, we can have this property. We have this property coming from quantum dialogue function. So if we deform this mu above to imaginary, adding a non-zero imaginary part, and also put an exponential of beta. Yeah, this beta and alpha is kind of conjugate to each other. And then you have asymptotic behavior of this quantum dialogue function when mu goes to infinity and mu goes to minus infinity. So it has this kind of behavior. Then you can see that this function, once you put exponential, is a Schwarz function if you introduce alpha and beta. And then if this alpha beta is inside a open triangle, okay? So it means that alpha beta has to be smaller than Q divided by 2. And this Q are just B parameter relates to Weber-Emis parameter. Okay, so this is in case alpha beta both positive and also the sum smaller than the Q. So this is the open triangle. This is open triangle. Okay, so once you choose alpha beta in this open triangle, then this function is a Schwarz function.
Psi delta somehow modular.
Yes, it is. It relates to modular form. So what Danzage called quantum modular form. Yeah, it relates to that. Okay, and then so the alpha beta, such that this quantity is Schwarz function, is called a positive angle structure of the three manifold. And so yeah, in this case, all the positive angle structure form a open triangle, satisfying this inequality. Okay, so why we're looking into that? Because when we consider Fourier transform of this quantum dialogism, and this Fourier transform is convergent absolutely if the integration contour is shifted away from the real axis and by alpha, and such that this alpha beta belongs to this positive angle structure. Okay, so that's the motivation to introduce that. Okay, and now let's go one step further, because we are going to glue tetrahedra to form an ideal octahedron. And it has 5 ideal tetrahedron. And the partition function is just a simple product of four ideal, sorry, it has 4 ideal tetrahedron. Then the partition function is just a product of 4 quantum dialogues and subject to a constraint, because there's in the middle, there's an internal line. relates to a constraint. And then you can do the same thing to study asymptotics of this function. And you find, once you put the exponential in front, and this function is Schwartz function, if you have 3 mu's, and if you have 6 parameters alpha beta, and if these 6 alpha betas constrained by a non-empty open polytope. So here you get, it's a higher dimensional polytope, and this is really a non-empty. So here I show a cross section that in case all those beta and all the alpha are the same, and then you see there's then it's become a triangle, and this the area inside the triangle means it is a positive angle structure. Okay, so once you have a positive angle structure, so all the alpha betas inside this open polytope is a positive angle structure of the ideal octahedron. Okay, so then there's a theorem proved 8 years ago, that the partition function of SL2C Chen-Simons theory converge absolutely if the 3 manifold admits a positive angle structure. So here we show that, in this at least tetrahedron and octahedron, there is a positive angle structure. So the Chen-Simons theory is well defined. Okay, so now let's move further to glue those ideal octahedron. Okay, and to form this 3 manifold. And then the Chen-Simons theory on the graph complement 3 manifold are, as I said before, are just some Fourier transform. So basically, you product the octahedron partition function and make some Fourier transform. The formula, if I write, will be long, so I'm not going to write it. But the basically is just a Fourier transform of that function. Yeah, and in the end, and this Fourier transform will give a in the end, it's just a finite sum of a 15-dimensional integral and what usually called a state integral model for SL2C Chen-Simons theory. And then the space, it is not hard to check that the space of positive angle structure is not empty because it is simply just 5 copies of octahedron positive angle structure. And then this partition function converge absolutely. Okay, so now we are basically, finish the quantization of SL2C Chen-Simons theory. We get well-defined finite partition function. Okay, so now we are going to impose simplicity constraint. Okay, again, this is the key formula that we relate the flux of B to a magnetic flux of Chen-Simons connection on this triangle. Okay, and then in this case, the magnetic flux will relate to holonomy. Okay, so you can compute the holonomy around the triangle. And then by this formula, you get this is just exponential of B. Okay, this holonomy is holonomy of Chen-Simons connection. And then we know, so there was long, 10 years ago, there was a lot of study on simplicity constraint, and we already clear that we can discretize the simplicity constraint on each tetrahedron. And then the formulation of simplicity constraint becomes that there exists a time-like normal, okay, such that the B field has to be normal, orthogonal to this time-like normal for all the tetrahedron phases. Yeah, for each tetrahedron, there are 4 phases. The simplicity constraint just says that the B field has to orthogonal to a certain time-like normal. Okay, and then here the tetrahedron corresponds to a node. Yeah, and then the neighborhood of this node actually cut the graph, cut the 3 manifold, and the boundary of this region is a 4-hole sphere, and the hole are created by the effect. Okay, and then these translates to Chen-Simons connection that all of the 4 holonomies of the tetrahedron, holonomies around those holes, has to be conjugate to SU2 simultaneously, because this B is a space, it's a spatial orthogonal to a time-like normal, and this guy has to be conjugate to SU2 instead of SL2C. Okay, and then here we define the simplicity constraint for the model with cosmological constant, that the simplicity constraint restricts the moduli space of SL2C flat connection on 4-hole sphere to the ones that can be gauge transformed to SU2 flat connectors. That's the simplicity constraint in this context. Okay, and then this simplicity simplicity constraint can be decomposed into first-class components and second-class components, like I said earlier. That firstly, the first-class components of simplicity constraints are easy to extract because they are just eigenvalues of those holonomies. So this OF is the holonomies around the face. And because they has to be conjugate to SU2, then the eigenvalue has to be of U1. Has to be U1. Okay? So therefore, this lambda is the eigenvalue, has to be exponential of some, sorry, I missed an I here. So exponential I times some real quantity. And this real quantity actually relates to the area. And where area divided by the Chern-Simons level, where the area, well, Chern-Simons level relates to cosmological constant. So this is actually the area measured in cosmological scale. And then this J, which is the quantum area, it has a cutoff because it's on the exponential because of periodicity. This J has to be cut off by J minus 1. There's a, so the real part of the T. The real part of T. Okay, and so
you have gauge variance because you're talking about gauge transformation. You have gauge invariance.
yes, in Chern-Simons theory, so all the quantities so far we are talking about are already gauge invariant. So, for example, we are talking about the eigenvalues of the holonomies, and so on, and the conjugated variables. So all the quantities we have talked about. Okay, so maybe
Conservation condition. Invariant, does it imply a conservation condition? Conservation, for example, in the usual thing, you have conservation of charge.
Yes, that's right.
Yeah,
that's right.
The conservation in that case.
Well, the charge here will be, for example, the charge are precisely this quantity, this J. Yeah. Yes. Right. Okay. So in this case, and since we constrain the exponential, constrain the eigenvalue and relates to exponential of area. Okay. So here, yeah. So this actually one of the key points is that the area is bounded. This J is discrete, and also it is bounded from above. So in the end, it becomes a sum, bounded sum. It is absolute value. Sorry, I missed absolute value. Yes. Yes. It is. Yeah. This is actually absolute value. That's a good remark. All right. So yes. Then we need to impose this constraint, but these constraints are first class because all those lambdas are actually mutually commute. So by Chern-Simons symplectic form, you can check that these are all mutually commute quantities. And actually, the Chern-Simons partition function explicitly depend on those lambdas. And then how you impose a constraint, you just impose it in the wave function easily. Yeah, and the Chern-Simons partition depend on all these lambda f's and also depend on some other quantities and relates to the moduli space of flat connection on the photosphere. This relates to the second class constraint. Right, and then here there's an interesting phenomena which intertwine mathematics, where this is like a back reaction of physics into mathematics. That because we know they are positive angle structures, right? And these are usually some quantization ambiguities of Chern-Simons theory. Yeah? But so here we can kind of give a restriction to those positive angle structure by using the condition that we ask a 4-dimensional area at the quantum level equals to 3-dimensional area. And it turns out that this equation, this is complete physics motivation, physics consistency, and it gives a constraint to this positive angle structure. It's remove. So in total, there are 30 parameters for this free manifold. It's restrict 10 parameters. So and this actually we have used that in the usual Spinfoam model already. So this is actually an analog of similar consistency condition in the usual EPRL model. All right. So now this is the first class constraint is easy, and the second class constraint is less trivial because if we fix all the lambdas and then the second class constraint, we should constrain the moduli space of SL2C flat connections on the 4-puncture sphere or 4-hole sphere to the moduli space of SU2 flat connections on 4-hole sphere. On the left-hand side, it's a non-compact space for 4 real dimension, 2 complex dimension, and the right-hand side is 2 real dimension. It is a compact symplectic space. Yeah. So both of them are symplectic space. So here this constraining both the position variable and also momentum variable. That's why it is the second class constraint. And so here the trick is that we are going to use, so we are going to impose the second class constraint to Chern-Simons partition function, and we are using coherent state. So we are going to find the coherent state in, so I'm not going to talk about the details in constructing coherent state and so on. So, but the scheme is that we find the coherent state in the Hilbert space, and then we express the Chern-Simons function, Chern-Simons partition function in coherent state basis. And we just compute the inner product. And then here, this coherent state space, a coherent state label rho, it labels a point in the moduli space where this coherent state is picked, because the moduli space is a symplectic space, and this rho is labels a point in the symplectic space. And we just impose the semi-classical constraint, second class constraint to the coherent state label rho. So we have the class of constraint labeled by rho in the moduli space of SL2C, and then we just restrict the class of constraint such that this rho only inside the moduli space of SU2. Okay, and the resulting the restriction resulting this inner product, and this formula, this quantity is what we call spin-form vertex amplitude. So this is the vertex amplitude we use in quantum gravity, and then this is now a finite sum of an absolute convergent finite dimensional integral, because this quantity Chern-Simons partition function is absolutely convergent, and this quantity is absolutely convergent as well. All right, so now we can construct the full amplitude. Okay, and for any simplicial complex, four-dimensional simplicial complex, we have all bunch of faces, all bunch of tetrahedra, and all bunch of simplices. We just make a product of all the simplices, product over all these vertex amplitudes, and also make product all the phases and certain choice of phase amplitude, and sum over all the intermediate states. And the intermediate states are labeled by spins, by J. And now, but this J, as I said earlier, it only take finite range of value. There's a cutoff given by the Chern-Simons level, and Chern-Simons level relates to cosmological constant. And there's this rho is a coherent state parameter, coherent state label. And then we need to integrate over the moduli space of SU2 flat connections. And then we are able to prove the theorem that, because the key point is that because this vertex amplitude is finite, then, and this sum is finite, then provided that there's no singularity, provided, and suppose this measure is regular on the compact moduli space, then this full amplitude is finite. So this is something we proved last year. Okay, and then here this shows the finiteness of the amplitude, because we introduce cosmological constant. Indeed, the spin-form amplitude is finite. And then here I also I briefly introduced the semi-classical approximation. So here we can also study the semi-classical asymptotics for the four simplex amplitude. And the semi-classical limit is given by this kind of double scaling limit, namely the area goes to infinity and also cosmological constant goes to 0. It means that you scale your area, but at the same time you scale your cosmological scale such that the area not go beyond the cosmological horizon. Okay, so such that, so this J times lambda is fixed. Okay, and once you do this limit and you look at this integral, and you find this limit are just one should use stationary phase analysis. It put the integral in the standard stationary phase form, and we should use stationary phase approximation to study the limit. And then we need to impose certain boundary conditions which are related to J and rho. And then if we use the boundary condition, then suppose this boundary condition corresponding to a non-degenerate four simplex, and then the integral has two exactly critical points by the stationary phase approximation, and those two critical points correspond to the same constant curvature four simplex geometry, but with opposite orientation. And the asymptotics of the amplitude is given by two oscillatory phases, and each of the phases are precisely the exponential of Regge action, or exponential of minus Regge action of this constant curvature four simplex And there is an undetermined constant, which is independent of geometry, and usually what we call, it relates to something called Maslov index. Yes, and then this the action is the Regge action with cosmological constant. All right, so now let me summarize. So here we construct the four-dimensional spinfoam amplitude with cosmological constant, and the point is that we use the stationary the state integral model of Chen-Simons theory, and the spinfoam amplitude we get here are all finite. So because of stationary phase, because of the state integral model, it is finite dimensional integral, and we are able to prove that the amplitude is finite. And moreover, the asymptotics, the semi-classical behavior of the four simplex amplitude reproduce four-dimensional Regge calculus with cosmological constant. Okay, so these two properties shows that this model so far is the best four-dimensional analog of Kurayev-Viro model. And some future task is, for example, we can consider the small lambda limit. So in spinfoam, so in principle, it should recover some degree of divergence if we send the lambda goes to 0. And this is something called a radiative correction in spinfoams. It's interesting to understand this degree of divergence. And also, I mean, it's interesting to study numerics in this spinfoam model with cosmological constant. Now this model is just some finite dimensional integral, and all the numerics in spinfoams can be applied. And we should numerically compute the critical point and also apply Lipschitz symbols. And also, there should be some relation with bulk boundary duality, something people usually call ADS-CFT correspondence or gauge gravity correspondence, because you see this is like a four-dimensional gravity. It relates to a three-dimensional Chen-Simons theory on the boundary. So there may be some relation to the bulk boundary duality. Yeah, I think that's all for today. Thank you very much.
1.5 hours, so if you need to leave, now's a good time. Otherwise, if there are questions for Muxin.
About simplicity constraint, where it came from and why we have to impose it.
Yes, so it's because so we are working on topological quantum field theory, right? But we want to work on it should relate to gravity, yeah. And because gravity is not topological quantum field theory, yeah? And then this constraint just a bridge to translate, I mean, to constrain the topological quantum field theory, and to make it relate to gravity.
It's just was taken from outside. It's
not from. It is not inside the topological quantum field theory, but it is inside quantum. It is inside gravity. So inside gravity? Yeah, inside gravity. Yes, you have to impose this simplicity constraint in order to get gravity. Otherwise, it's just topological quantum field theory, yeah, and which is not gravity.
So work vice versa. I mean, you can start. The point is that if you start with gravity, and you massage it, you start writing the Tarski formulation, and you want from gravity to relate to this theory of what you have to do is to undo the constraint.
Yes.
So I mean, you work from top down, but usually, like from gravity, you go down to logical theory. But knowing that, then what is like starting from logical theory,
right?
And he knows how.
Back to gravity.
Physical meaning constraint.
It's constrained because we know the gravity degree of freedom are metric geometry, and it is our tetrad frames. But this B is a two form. It's a Lie algebra value of two form. So and it has to relate to metric or relate to tetrad, and that's why this B equals to E wedge E. It's a wedge product of tetrad one form.
That's the mathematics.
Oh, yeah.
Then there is also the physical answer, physical interpretation of it. You put yourself in time in a particular gauge, that we call it the time gauge, then the simplicity constraints the relations in rotations.
Oh, yes, that's right.
Between the relations generator, sorry, the generators of this gauge should be proportional.
Yes.
But it's not what you described. It's not constrained. It's a relation.
It's a relation that appears in gravity.
Yes.
Yes.
My opinion, constraint that is some restriction for hospital on the side.
On B, yeah. B is a linear combination of boost generator and rotation generators. And then the constraint says that these two generators are related, are proportional. So this is a constraint.
These states, coherent states, would they be somewhat similar to quantum optics coherent states?
Yes.
You recover
Yes.
them in the, as in for
Oh, these coherence, you mean the coherent state we use to imposing simplicity constraint? They are very similar to oscillators. So it has, because you see the partition function depend on two parameters, mu and m. One continuous, one discrete. So this is actually a product of usual harmonic oscillators on like quantum mechanics on real line, and also a coherent state for circle.
related to global state.
Relates to
Global state.
Glauber states. Glauber states are just the coherent state for quantum mechanics. Yes. Carlo?
So is this your condition you had for the flux for the Chen finance? Is it a generalization of the Gauss-Bonnet type of relation?
Gauss-Bonnet relation. No, I don't think so. No, this is just so you are talking about this, right? No, this is not this. No. Yeah.
Stokes.
Yeah, this is Stokes. Yeah.
Stokes.
Yeah.
Very curious about the numerics in our group.
Yes. Yes.
You too, your group.
Right.
So I wonder, so how do you see this going? So first of all, so here there are no quantum groups. Just how easy or how difficult would be to.
So this is like yes, you have, so for this, the integrand has 30 variables. 15 are continuous, 15 are discrete, and you sum over the 15 discrete variables and integrate over 15 integrated continuous variables. So this is a sum of 15-dimensional integrals, and everything is explicit. You can write down this. I mean, you see this. The only thing a little complicated is quantum dialog function, but but it's not complicated. It's just a meromorphic function, so it's not complicated. And the integral doesn't see the pole. So so it's well-defined formula. You can write it down on a piece of paper. No divergence at all. Yeah, this is for simplex. Yeah, and then if you have multiple simplices, then you have extra integral of this rho parameter. You need to define a measure on the moduli space, on the compact moduli space. Yes, you have some additional integral for gluing for simplicity.
This is something you can already.
No, it was done last year. So this is.
I was thinking if the model with standard.
No.
In that case, it was always just a single.
Oh, that one was even not for the single. That one was using path integral. So there was a formal formulation. So that there's no way to apply concrete calculation for that, because that was a path integral. Yeah. Here, yes. Yes. It's just finite dimensional integral. Yeah, Carlo.
For the finite it's also finite.
Right.
So it's really a finite.
That's right. That's right. Yeah.
Because
Right.
the bubble, there are no bubbles here.
There's
There are
no.
no divergence.
Yeah. There's no divergence. Yeah. So I mean.
This really gives a sort of finite return.
Mm-hmm. Right.
And is n equal n plus?
What?
N plus equal
N plus? What is
the
N?
last equation when you have these topics. The two.
Whether N plus equals to N minus. Complex conjugate. Complex conjugate to each other. I think. Yeah, I think complex conjugate.
I admit that I was always confused by the, even if you have a negative, because if you have a positive logical, from point of view of a physicist, it's easy to have an why it's a
Mhm.
and it was not clear to me how a negative logical constant have also provided that. But
Yeah.
the fact now you are telling me that
Yes,
okay, there is
yes.
this
Yes.
absolute values.
Right.
that
Right.
appear,
Right.
so
Right.
that-
Right.
I think this is
Yes.
it's very
So-
interesting and
right.
new one.
Right. The point is that for the SU2, you can talk about curved tetrahedron and on the sphere or hyperbolic surface, all unified in the SU2 moduli space of flat connection. Using SU2 group, you can talk both hyperbolic space and the spherical space.
When you have the dark energy, does it correspond to an universe accelerating? Would you be able to get that kind
Yeah, that would be nice. So it's something we should do. Something we should do. I mean, you see, this was done last year, and we are putting this amplitude in a computable form. Then the next we are going to apply techniques.
In a sense, we are always producing the cosmological constant by hand. So
Right.
the logic here is that cosmological constant is part of the theory of gravity there. It's not like an emergent cosmological constant, so that you derive. It's more that you make the theory consistent with what we know already about gravity.
Right. That's right. That's right. So here, lambda, well, at least we call the bare cosmological constant, and this is a fundamental constant in quantum field theory, in quantum gravity. Yeah. Oh yeah.
So actually, the 3D gravities we use at of the lecture, the cosmological constant associated with the quantum group as so it's an unrelated four-dimensional also.
So this is something we want to look at. So at this moment, it seems to okay. So there's a candidate. There's a quantum Lorentz group. There's a quantum Lorentz group is okay. So some well-defined quantum Lorentz group is okay. So your question relates to this. Okay. So we study this quantum Lorentz group, but this quantum Lorentz group has a feature that the Q is a real Q. The Q deformation parameter is a real Q. Okay. And then there is a known relation between SL2C Chern-Simons theory for quantum Lorentz group, but that SL2C Chern-Simons theory has pure imaginary coupling, pure imaginary level. But here we see that we have to include both imaginary part and the real part of the Chern-Simons level. So which means that it doesn't really relate to the existing known quantum Lorentz group, but it may relate to certain, Hopf algebra, but this is not clear. Yeah.
Another question is, without the constant, the y to stress on SL. How does we y maps?
Oh, this Y map is encoded in the coherent state. So the Y map is used to solve the second class constraint. Yeah. So here, this Y map is basically the coherent state and take the projection.
Right. Again.